our discussion with a little sort of, let's see, what would we call it? Reflection on how hard it is to have everything go just right. So, you had 2 bags with 2 reactants in them. You ran a chemical reaction. It's a really simple chemical reaction. It's every 5-year-old's favorite chemical reaction, baking soda and vinegar. We can write the equation for it. We will later. We'll actually write the equation, look at the products, balance the reaction. But for today, we're just interested in the fact that it's a reaction. And the conservation of mass, law of conservation of mass, says that the mass in that sealed bag should remain identical. So let's just think about this, and we haven't done chemical reaction equations yet, so I'm just going to do this. Baking soda plus vinegar, and we could actually be a little bit fancier than that. Yeah, I should be a little bit fancier than that. Cancel. Anybody know the chemical name for baking soda? Sodium bicarbonate. Can't spell. Sodium, I'm going to abbreviate that to bicarb. Plus, do you know what the active acid ingredient in vinegar is? I mentioned it earlier, but you may not have caught it. Acetic acid. So, and we're not going to do formulas or anything on this, but this reaction, and by the way, this is a solid, this is a liquid. What does the reaction produce? You may not know the chemicals it produces, but what's the state of matter of at least one of the reactants? Oh, it's a gas, yeah. So what we produce is actually sodium acetate, and we get a little bit of water as a byproduct, and we get a whole bunch of carbon dioxide. So we get gaseous CO2, and let's see, can I do this? Probably not. Let me shrink this. There. That looks like Cu. So we get gaseous CO2, we get some sodium acetate, which is probably mostly in liquid form. I'm not really sure. We get a little bit of water in liquid form. It's not like groundbreaking, earth-shattering chemistry of any sort. We all know that. That CO2 gas, however, and this is what makes it so appealing, such an appealing reaction for 5-year-olds, is because it makes bubbles. Anytime we create an insoluble gas, we get bubbles. That's how we know that's one of the ways we know a reaction has occurred. So, in the open bag, where does that gaseous CO2 go? Out. It's just lost to the atmosphere. It's gone. So what we know is in that open bag, we would expect to see a reduction in mass because we lose this gaseous product because the CO2 is lighter than all the other stuff that stays in the bag. Now the goal, of course, was that in the closed bag, what would happen? The CO2 would stay in there. The mass would be unchanged. Yay! Look at us. We proved the law of conservation of mass. Did anybody actually have that work out? Didn't think so. So it's hard to get everything to go just right. And that was very much, do not get me wrong, that was very much like kitchen table chemistry. Seriously, we're using baking soda, vinegar, and plastic bags from Aldi's. It couldn't get much more kitchen table chemistry than that. But think about the kind of tools that were available to people prior to the 1700s. They didn't even have plastic bags. How do you run a reaction in a sealed vessel? Now you squeezed all of the air, as much of the air as you could out of that bag. You tried to not allow any of the gases to escape by using the funnel, by being very careful, by tightening that opening. How do you run a reaction in a sealed vessel in 1770? It's tough. Honestly, you do it by creating your own glassware, putting your components in the glassware, then melting the glassware shut. Seriously, that's how they would have done it, to make a sealed vessel. That's the only way to do it. You wouldn't have been able to do it with the baking soda vinegar reaction that we ran, the acetic acid sodium bicarbonate. So it's actually tougher than we think to measure things perfectly and to make things go perfectly. So I just wanted to kind of put in context that whole quantitative revolution in chemistry took a lot of observations from a lot of people, and it took a lot of really, quite frankly, people who were probably anal retentive jerks about measurement. Because that's what it takes to get perfect measurement. Now the second part I think went better for people. Did everybody gain a little bit of mass on the magnesium? Okay. So here, what we should have seen, of course, was in an open vessel, a loss of mass. But in the other case, we saw a gain of mass with seemingly just that magnesium. Now, you and I know what happened. What happened? Do you know what happened? It magically gained phlogiston. What happened? Was what was left in the end just magnesium, or was it something else? Good question. What was that product? I'll give you a clue. It was not just magnesium. Something had combined with the magnesium. What in the air can combine with magnesium? Oxygen. Yeah. Well, what you ended with was actually magnesium oxide. So where you had just magnesium atoms to start with, you now have a compound at the end. So you've added mass because you've chemically bound oxygen to the magnesium. That's pretty cool. But how confusing is that for people prior to the chemical revolution to see that some things, something happens and they lose weight. Some things, something happens and they gain weight. So it really was pretty revolutionary, the kind of observations that were made about quantitative chemistry. And that moves us to John Dalton, our school teacher. Actually, let me stop that one video. We'll call that lab debrief.